So how are you guys enjoying the conference? You positive? This is my last talk of the week. So I started off the week feeling a little rusty, a little nervous, getting in front of people, and then by a couple days ago, 3 or 4 talks into it, I was in the zone, and now I'm in my final and 7th talk, and I'm basically dead inside. So I'm going to finish this. We're going to have a great final session. Then I'm going to go back to my hotel room and kind of hang out in the fetal position in the shower for the rest of the week, I think. So there's a lot of content to cover. We're going to start officially like in a few minutes, but just to kind of introduce myself and things and set the mood. So this is my most popular talk, and I'm really thrilled that it's finally going to be recorded and put online for once. I kind of, I hope that that's the fact that I did a good job putting it together, but I kind of secretly suspect that most of the popularity centers around the fact that it uses the Raspberry Pi, which everyone seems to love. When we make up sessions and we come up with content, we try and get stuff that people are going to be excited about and that is interesting and trendy and all that stuff. So, first thought is something along the lines, I have no idea how to, here's my clicker. So first thing is maybe something like this. I could do like an IoT microservice DevOps in the cloud, of course, autonomous. The problem is I really don't know what most of those words mean. So you're stuck with me talking about the JVM for the next 45 or so minutes. So that said, about me, I think it's time we can officially start, I guess, as people file in. I know, right? Well, I clarified that because someone actually asked. So, I'm a huge fan of Taco Bell. I tend to go to most of the new Taco Bell store openings around, certainly in the major Tokyo area. And they have a mascot. They all know me. They're kind of creeped out by me. But yeah, that's me. So my day job is I'm in the sustaining engineering team. I fix HotSpot bugs. I'm on the update. I'm one of the maintainers for the OpenJDK updates project. I do a lot of evangelism stuff on the side. I wrote the JRocket portion of the Japan's best-selling WebLogic server book. I tweet, I blog sometimes when I'm in the mood. Yeah, that's me. So today, program agenda. Yeah, we're really close enough, 59 after. So we're going to go through and just kind of talk about what we're going to talk about, give some background to stuff. And then I kind of like to just go off and talk about things that have no real practical applicability to our day jobs whatsoever. And one of those will be talking about special relativity. Then we'll go through a little bit of the history of the memory model. This is basically a memory model talk. And then we'll get into the real meat of the talk, which is the implementation. Under the hood, how do we make the memory model actually true for your code when it's running on the JVM? We'll talk a little bit about the future, not too much, just kind of what are some open problems, so to speak. And then I'll leave you with some takeaways to go home and worry about. So time and time again, one of the major motivations for this talk is I keep running into developers that say, well, I don't write multi-threaded code, so that's not, the memory model's not really a concern for me. But if you write anything like Java EE, application servers, web servers, that's multi-threaded. If you write GUI code and you're dealing with the event dispatch thread and every other thread that you are running tasks on, that's of course multi-threaded, and you have to be aware of the threads and how they interact with each other. If you write libraries, maybe you think your library is only being used in a single-threaded manner, but your users definitely won't guarantee that. So, and then batch processing is kind of the textbook example for running on multi-cores. And maybe you're not writing multi-threaded code for your batch processing, but if you're not, you're probably giving up a whole lot of performance, and you should be writing multi-threaded code. So basically, everybody is writing multi-threaded code. The really worst case scenario is where you're writing multi-threaded code, but you don't realize that you're writing multi-threaded code. And then that's when all sorts of really bad things happen. So we have what are, of course, known as race conditions. Here's a simple circuit diagram example. So we have a NOT gate and an AND gate, and each of these gates has some sort of propagation delay. So there's a time when we change the signal here that it takes for it to be reflected on the other end of that gate. And because of the propagation delays involved, you can actually, when you change the signals, there's a moment where A and not A is true, which, at least that's what the output tells us. So we have to be aware that these race conditions exist and avoid them. This is obviously a circuitry example, but software has a whole lot of similar things. And what happens very often when we have these race conditions is we have some form of what I call Heisenbugs, which are the bugs that display this Heisenberg effect, where they happen in production, but when you try and run them, or even reproducibly in your local environment, but when you try and run them in a debugger, all of a sudden they disappear. They're intermediate and they're very timing dependent. And so anything you do to try and gain visibility into the problem changes the timing enough that they just kind of go away. So we want to avoid these Heisenberg bugs that are kind of a result of the observer effect. And our tools to do that are basically the Java memory model, and specifically the synchronized keyword, which gives us the intrinsic locks, the Java monitors that we've had as part of the language specification from day one. And much later, the Java util concurrent package and all the utilities and primitives it gives us to build synchronization into our code. And I'm sorry, the template really butchered that. But if you can read this, it says don't do XXX and you must do YYY. So these are like just basically rules that you want to follow or best practices that are derived from the memory model. And lots of Java developers kind of know, like, oh, there are these different rules about how you do critical sections and how you manage shared state and stuff. But very often we don't know why those rules exist. And so one of the goals of this talk is to kind of go into the background and give you some reasoning. Because when you just memorize a rule, sometimes it's very easy to forget. And you don't understand it on an intuitive level. You can't expand from it, and you don't know kind of what the scope or limitations of that rule might be. But when you understand why that rule exists, and you do understand it on an intuitive level, then you're much more prepared to kind of deal with things that go bump in the night and exceptions and all that other stuff. So for background, the memory model, there's a bunch of different definitions for memory models. If you go and you ask 10 people, you'll get 10 different definitions for a memory model. One of the definitions I tend to like is some sort of system or guarantee that says, okay, if you make a write into memory at some point in time, what are the conditions where we can guarantee that another read, possibly done by a different thread, will reflect that write? When will you see the writes that you make? What are the rules that guarantee that writes become visible to other threads? That's one definition of the memory model. And so in practice, let's think about this. So we have this Hoge method one, and I have a local variable here. I have a local 32-bit integer, and I'm assigning it 42. And then I have assert here. And the first question is, is there any possibility that this assert will actually catch or be thrown? Or I don't even know what asserts do because we never enabled them. But say we actually had asserts enabled in this environment, and we run this. Is it possible for this assertion to be thrown? Anybody? A guess? It should not. You're right. It should not. Hopefully, unless there's a horrible bug on the JVM side, it won't. And the reasoning is because your local variable is in your stack, right? Your thread stack. This is somewhere in the activation frame for this method on the stack of whatever thread is executing this. And if you have threads that are kind of messing up and writing into each other's stacks, then you're in real trouble. That normally doesn't happen. So the Java memory model tells us that this should be a safe bet. There's no way that a local variable could be kind of overwritten right under your nose. Let's look at a different example. And for this one, just to be clear, this doesn't necessarily need to be static. I just, for some reason, felt like making it static. But even if this wasn't static. So this is no longer a local variable. This is a field for this particular class where this method is defined. So in this one, is it possible for us to assert here? Yes, right? So if someone else, if it's possible for a pointer or reference to escape, and for another thread to get access to it, which is certainly the case if it's a field of your class, then yes, you can get overwritten. And so depending on what the other code does, this assertion may actually throw. There's no guarantees there. Okay, let's look at something a little more interesting. Let's say we have a flag here, and this flag is called ready. And so I'm using this flag to signify whether the data is ready to be read or not. And the data in this case is conveniently named data, but this data here, this Hoge4 thread at the bottom here is going to write the value 42 into data. And then it's going to set the flag. And, so it's basically saying, hey, I've written the data. It's safe to read now because I've written it. And then Hoge3 in the middle here, that's just in this busy loop, this while stuff. So it's waiting for that flag to be set. And as soon as the flag is set, then it goes and it reads the data, compares it to 42, and throws an assertion if we messed up. Can this assert fail? It can fail. It can definitely fail. It's allowed to fail. That's part of the Java memory model specification. It very often won't, but there's no guarantees. So why do we have these kind of problems? Well, there's several actually parties that we can blame. One of the first parties is, of course, JIT compilation. So under your nose, the JIT compiler is going to take in the Java bytecode, and it can play really loose and fast with the order that things are done. There's all sorts of reasons that it might prefer one order over another, and that might be different from the order of operations that you specify in your code. And we'll go into detail about what those constraints are in a few more slides. But just in general, JIT compilation can change things. Another thing that can change things, even if at the software level nothing has changed, modern hardware has some liberty to go ahead and change the timing of things and to move the order of certain events around for caching and managing the pipeline and whatnot. So for example, if we just had code right here where I'm assigning 1 to A, 2, B, C, yada, 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 and at the very end of this, I take A equals A plus 1. I increment A by 1. Like, no optimizing compiler is going to look at this and not mess with it, right? Because this is very inefficient and stupid code. So one thing an optimizing compiler should do is it should fold this. It should basically be able to do constant folding here and say that, oh, A is going to be 2, and I know that right out the gate. And so the order that memory is written to and the values that get put into it is not inherently obvious just from a look at the Java code itself. The JIT compiler is perfectly allowed to change the order here to make code that runs faster. And there's more than one way that it could do it that's just as efficient, for example. I mean, it could write to A here, or it could wait until this point to write to A. But when you're writing to multiple values, they're not necessarily going to show up, so to speak, from the viewpoint of other threads in the same order. So the big constraint, though, is whether you're talking about the hardware level changes or compiler level changes, is that single-threaded behavior can never change. So it's not allowed to change order. Like if there was a branch somewhere in this code over here on the left, where we're branching off of one of these values, what the thread reads itself has to be consistent with the original source code. So single-threaded behavior will always be, in isolation, will always conform to the code order, what you wrote, or at least it'll appear to conform to it. Because we're not allowed to change things in a way that would change the single-threaded behavior. It's only when you start asking questions about, so what do the other threads see, that all of a sudden things get complicated. So at the hardware level, we have pipelines. This is very simple. This is the classic pipeline where we have instruction fetch and then decode execution, memory reads, and then write back. And if as we're doing this at each stage, we want to do things like avoid pipeline bubbles. So if there's a dependency or something in the pipeline, the hardware has a really good motivation to go in and change the order of certain reads and writes so that we can kind of avoid the dependency and avoid a bubble in the pipeline. I mean, if you don't understand that, it's not really necessary for the rest of the talk, but just know that the hardware can do all sorts of sketchy things, but it has legitimate reasons to do so for performance reasons. With that said, what hardware is allowed to do varies drastically across different hardware. And so this is a chart I shamelessly stole from Wikipedia, but it's kind of showing you the different types of reorderings that different hardware can do. Generally speaking, there's, we think of weak memory models and strong memory models, or TSO models, and ARM and Intel tend to be stronger models, and everything else, especially in PowerPC and ARM most notably, tend to be a weaker memory model. So you have this kind of spectrum of stuff, and even worse was Alpha was just kind of crazy. Alpha could do things that no other CPU would ever consider to be valid, and it's kind of nice to see it go on. But in practice, we have these, we have this kind of spectrum here from the middle to the right. And this rears its head all the time, because if you're writing your Android application or whatever, and you're running it on your simulator on your AMD 64 or Intel or whatever machine, and then you go and you sideload it into your ARM-based hardware, and all of a sudden concurrency bugs that were not happening in your simulator start happening. And the reason is because the actual hardware has a weaker memory model than what you were doing your development on. So you have to be aware of that just because it seems to run correctly on your Intel hardware doesn't guarantee when you move to a weaker memory model system that it'll continue to run correctly. And because of that, so today's demos and a lot of the more interesting parts of this talk are going to focus on the Raspberry Pi, because it's obviously based off of ARM, and so we can kind of show a whole bunch of bad, scary things that can go bump in the night on the ARM that I could not reproduce for you if I was doing this on an Intel machine. So how do we avoid these types of problems? Well, at the very low level, at the level that no Java programmer should normally have to think about, we have what are known as memory barriers. We call them, some platforms call them fences, other platforms call them barriers, but they're basically the same thing. Intel tends to prefer fences. And so what we do, this is the flag example that we were just looking at, where we set a flag, and so we have this busy wait, and then we read it here. I should have indented that. And then we have the writing of the data and the writing of the flag here. So if we stick a memory barrier here, which says, and barrier is, it's kind of an ambiguous term, because I'm talking here, we're setting a barrier that somehow prevents the compiler from moving things around, but also then prevents the hardware from moving things around. And that is very platform and toolchain dependent. But let's just say we have some magic thing here that basically says you have to do this before you do this. A barrier or a fence in general says that you can't cross this line. You're not allowed to reorder things over this fence. Everything up until this point has to be done and committed in a sense before you're allowed to do anything after it. So we can put a barrier in there, but actually that's not enough, because just writing it, guaranteeing that these writes are reflected into, say, like main memory or something, or cache is flushed, or a write buffer is flushed in time, would not necessarily guarantee that we would read in the same order. So generally speaking, you need, when you have a read and write scenario, you need barriers for both. You need a barrier when you read, and then you need a barrier when you write, and then you need another barrier when you read. And that's the only way to guarantee that when this thread reads this flag, and this flag says, hey, the data's ready, that yes, the data will definitely be ready when we get there. So there's actually all sorts of different barrier types. And a very common way of breaking things down is this kind of store, load, load, store, load, load. And those are telling you the different types of actions or operations that it prevents from moving over the barrier. So a load barrier would prevent loads from moving ahead of other loads that are supposed to happen later on down in the instruction stream. And at this point, probably at least a few of you are going, yeah, this is really complicated and detailed. So it's going to get even just a little bit worse, because then there's compiler barriers, and that's completely toolchain specific. And so these, obviously you have to know which barrier you use for whichever toolchain you're using, and these may or may not also translate to, opcodes or instructions for the CPU to do a barrier. So you're probably looking at this going, eyes glazing over, or being like, why do I need to know any of this? And the quick answer is you don't need to know this. Java protects you from this if you follow the memory model. But for now, let's just kind of take a tangent here and talk about something that's a little bit easier to understand. Special relativity. So I don't understand special relativity. And I actually gave this talk at one point where someone came up to me after the fact and was like, actually, the way I explained something was like really, really wrong. So this is not a physics lecture. I'm probably just making stuff up from watching way too much sci-fi. But this is how I like to think special relativity works, right? So we have these three events here. We have A, B, and C. And this person on the left, who was like way more better looking before I had to use this template, sees the order of these things and they go, oh, well, A happened, then B happened, then C happened. Then there's a person over on the right. And this person sees the same three events and says, no, that's not the order it happened. Actually, CBA happened. Like the two people witnessing basically the same set of events see two different orders. And so the observed order depends on the viewer's frame of reference. So where they are in space, which direction they're traveling in and which speed they're traveling will impact the order that they believe that things in the external universe happen. And there's not a right and wrong. Both of them are correct, okay? So this is actually disturbingly similar to what we have in multi-threaded code. So my job as a HotSpot engineer who fixes bugs is I very often get core files. And a core file is just a memory dump at the moment that something went horribly wrong. And we look at that to try and figure out what that horribly wrong thing was. And people think, well, it's a single snapshot. And so bam, instantaneously, this was the state of the machine when we went down. But there is no single instantaneous universal state of the machine. Every single thread, or at least every single core that was active at that time, might have had a slightly different view of memory. It's not going to be completely different, but there are limits. But there's not a perfect synchronization that just magically happens because we happen to generate a core file, or that we're looking at individual threads to see what values they see at any given time. So multi-threaded code is basically kind of like special relativity in a sense, where you have to, everything depends on, well, which thread are you running on and what are the guarantees the memory model gives us. So that brings us to kind of what another very useful definition of a memory model is. It's kind of a contract, almost like a part of the API. It's part of the language specification. It's saying, here's what you as the programmer can depend on. We promise that we're going to do all this crazy stuff in the background and change the order of things and whatever, but we're going to guarantee that these kind of problems can't happen. And if you follow these rules, then you'll be safe. So it also, in another sense, it's kind of a contract with the runtime implementers of what we're allowed to get away with. So some history here. I want to jump over this kind of relatively quickly just because of the time constraints, but I just want to point out that Java was really revolutionary in being the first language to incorporate multi-threading as a first-class member of the language. And so, previously, obviously, there's POSIX thread libraries, and but multi-threading and concurrency was always something you added onto the language as like an API or something. Java was the first major language to actually make multi-threaded and kind of assumed concurrency part of the language specification itself from day one. So we have this happens before relationship, and this is kind of the most important concept of the memory model. And I'm showing the Japanese page here just because I want to point out that this happens before, and this is almost like a proper noun. It's just like the keywords in the language and whatnot. It happens before, even in the translations we do to non-English languages, is still rendered as just happens before. So this actually comes from work that Leslie Lamport did, and he's really famous for a whole bunch of stuff. Really, really smart guy. But he did he also did LaTeX, which anybody who's probably done a master's or higher has had the misfortune of having to learn. But a happens before relationship is really quite simple. There's basically certain things that guarantee that we can say that this happened before something else. Really simple, right? And like I said, in single-threaded code, it always has to seem, at least to that particular thread, like everything's happening in source code order. So there's naturally, within the context of a single thread, there's always a happens before relationship between each and every individual instruction. Okay? But what gets more interesting is if we're talking about stuff that's running on multiple threads. So we have here, and again, we're using the flag example, where Hoge4 is writing the data, and then Hoge3 is going to wait for the flag to be set and then read the data. So what we want is we want some sort of happened before, happens before, those terms tend to be used interchangeably, to be established between these two things. And so one way we can do that is if we make the methods synchronized, then we are guaranteed that they are kind of run atomically. And so assuming that they're synchronizing on the same reference in the heap. And so this is one way of guaranteeing that this will run or this will run, but they won't run concurrently. And so all the effects, like say if Hoge4 runs first, then we're guaranteed that both of these writes are visible before anything is read here or anything's run. So if this runs and then this runs, we're fine. But if Hoge3 runs, then we deadlock because it's synchronized. It's holding a lock that Hoge4 is never allowed to acquire, and it's always waiting for a flag to be set that Hoge4 will never set. So this is not a solution to the problem, but it does demonstrate one case where a happens before relationship is established. So that's one way we can establish a happens before relationship between two threads, is to synchronize on the same monitor. So all of this is laid out in chapter 17 of the JVM language specification. It's not exactly the most entertaining and exciting reading that I've ever done in my life. But really, when you have doubts and when you're talking about and thinking about edge cases, it really is the definitive source of truth for this stuff. And everything I'm talking about today is based off of what's in this document. So the memory model itself has evolved and expanded drastically over the past, over the lifetime of Java, the past 2 decades. When Java first came out, the memory model actually only really dealt with the keyword synchronized. So synchronized would allow us to establish a happened before relationship, and that's pretty much all that we knew. It gave us mutual exclusion, obviously, and it would establish this happened before between two different threads, but that was pretty much all the memory model gave us. Volatile was also defined at that point, but all volatile did is it kind of told us some things about visibility. Like if you're reading a variable or a field that is declared volatile, there were certain guarantees about visibility that declaring it volatile gave us, but there was no happened before or happens before effects as a result of reading or writing volatiles in the old model. So this turned out to be quite a weakness. Having volatiles that really didn't impact, they had impact about their own visibility, but they gave us no guarantees about the order of what you read or write to them and what other values that were written or read from before or after your volatile read or write. So what we want to be able to do is we want to be able to use volatile values to synchronize across different threads, and the original memory model did not allow us to do that. Also, as final wasn't mentioned. So if I declare something as final, it should not be able to change, but in the original memory model, it could change. I mean, even now, if you're doing horrible things with reflection and stuff, you can make things change too, but if you're a nice person, they don't change today. And there are all sorts of optimizations on the JVM side that people wanted to do that were basically not allowed by the original memory model. And around this time, Doug Lee, who's kind of one of the most well-known people in the Java concurrent programming world, came out with this book called Current Programming in Java. And as part of that, he developed an open source library of concurrency tools that became very, very popular and allowed you to do really, really powerful things above and beyond what the intrinsic locks, the monitors that HotSpot gave us, were able to do on their own. So in Java SE5, otherwise known as Tiger, Doug Lee's library was actually incorporated into the JDK class library proper. So we know this today as Java Util Concurrent, but that was originally an open source project that was basically so useful and became so popular that it just had to basically become part of Java. And it's something kind of similar to like Jota Time did later. So the modern memory model was defined there's JSR 133, and in this we're saying that, okay, so volatile will establish a happens before relationship. And specifically when we write to a volatile variable, I'm saying that all the writes previous to that volatile variable write will be visible to any other thread that reads that same volatile value. And also in this change in JSR 133, we said that when you declare something as final, it's supposed to never change. Okay, so we've basically added to the scope of the Java memory model now, and volatile, in addition to just making claims about visibility of reads and writes to itself, it also now establishes a happened before relationship between it and other threads. And also final now gives us real immutability for some definition of real. So now let's look at this example again. This is the same flag reading example. And I want to take this flag and I want to use it to synchronize between these two threads. So I declare this value as volatile. And now when I write to this flag, which is volatile, and then I read it here, I'm guaranteed by the happens before relationship that everything I wrote up until this point will be readable by everything that comes after this read. So volatile no longer just has an impact on itself. It allows you to synchronize the reads and writes that come before and after it. And this is critical. This is what allows us to kind of build more complicated synchronization strategies on top of it. Now, just to make sure, because there's always people out there that get confused here, volatile does not mean atomic. So say, for example, we had some sort of situation where we wanted unique IDs to put into a database or something. And so I have something that I'm incrementing here, and I want every time I call this inc ID, I want to get a new unique ID. And in this form, I can actually end up with the same ID being returned to multiple threads. So it's not actually going to be unique. And that's because this one line of Java code will translate at the hardware level to 3 different instructions. We've got a read, modify, and write action going on here. And if multiple threads say ID is currently 3, and then multiple threads concurrently call this method, they can both read 3, they can both increment, read that into their register, increment it to 4, and then return that to memory. And so this gets set to 4 twice. And both return values are 4, and so this is no longer giving us unique values. So one answer is that I can make synchronized, not the most performant answer here, obviously, but if I declare this as synchronized, then I get rid of that problem. A volatile is not going to help you. It doesn't make reads and writes magically atomic, generally speaking. That said, there's another issue when we talk about reads and writes, and that is when we deal with 64-bit numeric values, specifically longs and doubles, that the original memory model does not guarantee that those will be done atomically. So you can get a situation if you're reading and writing to, say, like a 64-bit integer, that you do a read and you see half of the most significant bits, the 32 most significant bits, reflect one write, and the least significant 32 bits reflect a different write. And so you can get this mixed up in between version of a 64-bit number if you don't use some sort of synchronization. And interestingly enough, if you declare it as volatile, this is guaranteed not to happen, which is nifty. So like I said, there's several different situations where happens before relationship is established. One of them, like we talked about, is monitor acquisition and release. So, the synchronized keyword, when we would declare those methods as synchronized, because they were synchronizing on the same monitor, we had guarantees about when one method finishes and the other method starts, everything that was written by the first method will be readable by the second method. Volatile reads and writes, as we just saw with the flag example, establish a happened before relationship. When you freeze in a constructor, the object, you've basically established a happens before relationship with anything that's looking at the fields of that object. Anytime you jump into native code, anytime you jump into JNI code, whether that's third-party JNI code or just part of the JDK implementation itself, you have to have established a happens before, because in effect, when we call into native code doesn't really know anything about the Java memory model. So we have to guarantee to the native code that everything that it assumes is going to have been written is already written by the time we call into native. So people don't think about it too much, but if you do like a system out print line, you're actually forcing the system to kind of synchronize everything at that point in preparation to kind of jump over into native code. Any kind of input output, anything that crosses the Java native barrier will basically cause a kind of have synchronization impact. Threads starting and joining naturally creates happens before relationships between the threads that are doing the starting and joining. And then there's a whole bunch of operations that you do on Java util concurrent collections that give you these relationships before. So Java util concurrency itself, like I said, was added with JSR 166. So JSR 133 was the memory model update. JSR 166 is where Doug Lee's really famous and much loved open source concurrency library became part of the JDK class library. So we have all these different tools and these ways to achieve concurrency. And one question is, so what should I use? And generally, the idea is that you really want to be as abstract as possible. If you're going down and you're making different things volatile and you're trying to kind of use the most basic low-level primitives possible to cook up your own synchronization framework or whatever, you're going to mess it up. I mean, I'll just be completely blunt. The best way that I've seen this explained online is that Doug Lee gets it wrong. And if Doug Lee can get this stuff wrong sometimes, then none of us mortals have a chance of doing this. So, don't roll your own. This stuff is profoundly high performant, and it works, and it's tested. If you go down, have a really good reason for going down to a lower level. As much as possible, always use the highest level of abstraction available when you're talking about concurrency. So we're still going through the history here. With 7, we got fork join pools, which are a joy to use, I'm sure. We have JDK 8, of course. The main motivator for Lambda forms was, of course, that we wanted to have non-mutable, we wanted to be able to express calculations and stuff in these non-mutable forms that would be useful for taking advantage of multi-core processors and better. So in a way, that was a big change in the way we think about concurrent programming. And of course, with JDK 9, we have the introduction of Var Handles, which is new. And Var Handles actually kind of give us, from the Java API side, a even lower level of access than primitives like volatile and final. So for example, with the Var Handles API, what I can do is I can say that I want this value I want it to act like a volatile when I update it, but when I read it, maybe I don't care about it being volatile or not. And so an example there is that if we have like a read, modify, and write operation, when we do that because we want to make sure that we don't lose any updates, then we might want to be treating that memory location as a volatile. But if I'm just reading it and I don't care if my data is a little bit stale occasionally, if I'm not going to read and then modify and write back, if I'm just reading it for some heuristic purposes or whatever, maybe I don't care that it's the absolute latest version of that data. And so it allows you to be selective about when and under what circumstances you might treat a certain memory location as volatile or not. So that's just one of many examples, but basically Var Handles gives you this further under the hood almost level of access to primitives for synchronization. And the motivation behind this was that because we're trying to wean the world off of Sun-Mist Gunsafe, and Sun-Mist Gunsafe had a whole bunch of tools for letting people do stuff like this. And so if we're going to say, well, you can't use Sun-Mist Gunsafe anymore, we have to give people an official API that actually works and is supported and will be around for more or less forever, that they can depend on, that will do these things that they were using Sun-Mist Gunsafe for. And so Var Handles kind of helped fill that gap between what was officially supported by the Java API and what sometimes they needed to resort to using unsafe for. So here we're going into how this is actually implemented. And we're going to use in these examples a tool called HSDIS, or the HotSpot Disassembler. And what this tool does is it actually outputs the code that's generated from C1 or C2, so we can kind of see what it looks like. There's tons of stuff online about how to use these tools and how to build and use it. And there's actually something called a JIT watch that I think is probably a much more user-friendly experience. And if you want to play with this, I would probably recommend you checking out that. But that's not the focus here, but this just happens to be what I'm going to be using when we look at these demos here. So let's jump into the demos. But before we do that, because we're going to be looking at ARM assembly, and so we have to have some understanding of ARM assembly. So I'm going to give you the most unbelievably quick ARM assembly crash course in the history of humanity. Don't worry, it's going to be really, really, really simple. So in all the examples we're looking at, for all we really care about, we have an operation, we have a target, and we have a source in most cases. So if I'm like moving this literal value into register 2. So if you're thinking about in terms of what high-level source code that would look like, this is going to look like this. And if you think of with the equal sign here, this kind of helps you remember what I like to think of as like the Intel Microsoft assembly order, where what's on the right-hand side of the equals is on the right-hand side of your assembly here, and left-hand side of the equals is on the left hand, and that makes it very easy to remember that source, target. There is one exception to this, though, is that when we store from a register out into memory, for some reason it's the opposite order. But everything else besides stores that we're going to look at is actually this kind of traditional Microsoft assembler order of things, where we take the sources on the right side and target is on the left side. So let's look at just like copying values between registers. So I'm moving from the value that's in R03 and I'm putting it in R02. Or I'm taking 42 and I'm sticking it into R2 there. That's pretty easy to understand. Loads, this is RISC architecture, it's load store. So when we load, we take something from memory. So this is a memory dereference, and I'm taking whatever the value that's pointed at by R06 somewhere off in memory, and I'm storing that value in R03. And so this is just a simple pointer dereference. And then, of course, we need to be able to branch. So I'm doing a comparison here, and then I'm branching if these two values are equal or not. And this is equivalent of just this kind of if statement here, and then I'm going to do a jump to that. And then, of course, because we are talking about barriers or fences or whatever you want to call them, we have to know what ARM assembly considers a barrier. And they have these barrier data memory barriers, and there's like system, and I don't remember what ST stands for. Honestly, I don't really remember the difference between them, but it has both of those things. One other thing that you'll notice in the output is we have what are known safe point polls. And safe point polls, I've explained this in a few of my other talks this week, but basically is something that the emitted JIT code does on a regular basis to just to check to see if the JVM wants it to shut down temporarily to do a stop the world operation. So we're just regularly kind of checking in to make sure that we can do a certain read in a location in our address space. You don't have to think too hard about it, but okay, so let's go to our first demo here. We have 3 demos. We're going to go through them really, really fast here because we're almost out of time. So we have a long value demo here, and so I'm spawning 2 threads here. I'm using Lambda syntax. One of my threads is going to take this value here, and it's going to write basically all ones to it, because this is a 2's complement signed number here. So -1 is like FFFFFFF, ones all the way down. So one of them is just writing all ones to this value, and the other one's writing just all zeros to this. And then after I start those two threads, the main thread will hang out in this infinite loop, and it's going to just keep checking that value. So it reads that value, and it says, okay, I expect that value to be either all ones, meaning -1, or 0. It's going to be one of those two things. And if it's not one of those two things, then I'm going to stop and complain. So I think people are going to know where this is, how this is going to turn out. One of the things I did not anticipate by doing all this on the Pi is how difficult it would be if I didn't have the screen like in front of me that I could. So you're going to have to please bear with me here, but I think, oh. So this is it running that code. And you see very quickly we stop and say, hey, I discovered a 64-bit value where half of it is what one thread was writing, and half of it was what the other thread was writing. So maybe we can fix this. Can someone say what we should do to try and fix this? Yes, yes. Volatile. Yay. Is that? All right, so let's see if I have the right version of Java C on here. Actually, wait, I have a. Build. So I've just recompiled it. And with that one change, now I run it. And it's an infinite loop, and it'll never stop because it'll always be one of those two values now. It'll always be -1 or 0, and we're just bouncing between those. So let's look at the next demo. Well, let me do that. Okay, can people read this without me making it full screen? Okay, so object initialization. So I'm going through here, and I have an object in my constructor. I'm taking this one field number, and I'm naming it, not naming it, I'm assigning the value 42 to it. And so every time I look at this object, it should be 42, right? And in my main method here, I'm starting two separate threads. I'm starting one thread that basically does nothing but replaces that, right here, we have this pointer here, this global ref here, that's an object. And I'm replacing that with new ones. So I'm constantly allocating a new one, calling the constructor, and then pointing this global ref value to the new one. And then I have this other thread that goes and constantly looks at that global ref and looks at the number and sees if it's really 42. So I think you know where this is going as well. But, oh, I've had such great luck with live demos. Oh, I'm still in the infinite loop, okay. So here I stopped and it's like, hey, I found a value that was 0. That's what this code did, right? Is if it finds something that wasn't 42, it would stop and tell you what it found. And 0 is, of course, kind of the default value of initialized memory. So, or uninitialized memory, I should say, but that's been cleared out. So how are we going to fix this? Oh, this is the wrong, sorry. Sorry. Yes. So all I have to do is then recompile it. And then this is now another infinite loop that will just, thank you, I'm finishing right now. So one more final demo here, and this is the funnest one. So we have a loop, and in this loop, this should seem really familiar. We have a flag, and So in the flag, basically, we have one thread that's going to wait, and it's going to sleep for 5 seconds, and it's going to set that flag to true. And then we have another flag that's just going to spin on the value of this, and it's going to wait for that flag to finally be set true. So let's see what happens with this one. So here I'm using the client compiler, C1, and I start the loop, and it's 1, 2, 3, 4, 5. 5 seconds have passed, and we exited it. That's fine. What if we use C2? One 1,000, 2 1,000, 3 1,000, 4 1,000, 5 1,000. It's not going to stop. This is an infinite loop. So let's go ahead and take a really, really 10-second look at what the C2 compiler is giving us here. And you'll notice as you're looping around, we actually can see that we're actually not reading. We do the read here where we've read the value in, and we're looping around. But we actually end up getting into a loop where we're only doing the safe point anymore. I'm trying to find, so you can see there's a branch here, and this branch is actually not even, it's not a conditional branch anymore. All we're doing is a safe point pull anymore. So when we go into the code, we do a single read to check the value, but the memory model doesn't require us to go back and check because it's not volatile. So we do it with one-time read, and then forever we can just assume that that value will never change because it wasn't declared volatile. So this basically, it turns into an infinite loop. So even with the same JVM, depending on what settings you fire it up as, you can get drastically different behavior from your code. And so it's very, very, very important to follow and be aware of the memory model and all of its implications. Now, of course, the answer here is to declare flag volatile. I'm not going to show us doing that now because we're out of time. But anyway, so that's everything. I think I have yeah, there's still ongoing questions that we're working on stuff, and yeah, it's a work in progress. So try and stay low level. I'm sorry. Opposite. Try and stay high level. High level abstraction is just easier. Benefit from the work that's already been done by other people. Make sure you're coding against the specification. Don't do things like just keep adding volatile declarations until it starts working. Or sometimes you say this in so much code: synchronize new object, which people throw in just because it happens to result in fences in a lot of code. Don't do this. Know why your code works the way it does. For testing, you want to make sure, like we saw in this example, where you're testing as close to your production environment as possible because every little detail matters. That said, to make sure your code is good, test across all sorts of different JVMs, hardware, configurations, so you know that it's solid. And also read Brian Getz's concurrency in practice. This is basically the Bible of multi-threaded Java coding. Yeah, this is it. We're already out of time. Thank you very much. I appreciate it.